The following program is brought to you by Caltech.
Good evening. I am Ravi Ravichandran, the Director of the Graduate Aerospace Laboratories in the Division of Engineering and Applied Science. I would like to welcome you to tonight's Ernest C. Watson lecture. Today's lecture is this year's Richard C. Biederbach Memorial Lecture. Before I introduce our speaker for today's lecture, I want to let you know the next Watson lecture on March 19th, which will be given by Dr. Michael Lamb, titled When Rocks Roll, How Sediment Transport Shapes Planetary Surfaces. It gives me great pleasure to introduce our speaker for this evening, Dr. Dennis Kochman, Assistant Professor of Aerospace. He graduated from Ruhr University Bochum in Germany with a diploma in mechanical engineering with distinction in 2006. Upon graduation, he spent 1 year as a Fulbright scholar in the University of Wisconsin-Madison, where he was awarded a master's degree in engineering mechanics. He then returned to Germany and received the Doctor of Engineering from Ruhr University Bochum in 2009. After the completion of his doctoral degree, Dr. Kochman first moved to the University of Wisconsin-Madison as a postdoctoral associate in the Department of Engineering Physics. He came to Caltech in 2010 as a postdoctoral scholar in aerospace and as a Fyodor Leinen Fellow of the Alexander von Humboldt Foundation. He joined the Caltech faculty in 2011. Dr. Kochman's research comprises of theoretical, computational, and experimental mechanics of materials. His research aims to understand the scale-bridging relations between microstructure and macroscopic mechanical properties in a wide range of materials, metals, ceramics, and composites. Dr. Kochman's numerous awards and honors include a Career Award from the National Science Foundation. He has received the 2012 IUTAM Bureau Prize in Solid Mechanics and the Richard von Mises Prize from the International Association of Applied Mathematics and Mechanics. He is also a recipient of the Graduate Student Council's Teaching Award in 2011-2012 in his first year of teaching in Caltech. Ladies and gentlemen, please join me in welcoming today's speaker for the Watson lecture, Dr. Dennis Kochman.
Good evening, everyone. Thanks very much for coming. First of all, Ravi, thanks very much for these extremely kind words. We're here tonight to talk about materials. And for some reason, we're not seeing anything. We talked about this earlier today, that this never happened before. Here we go. We're here to talk about materials tonight. We live in a highly technological world where we are surrounded by materials. I'm sure many of you came by car tonight, some of these cars looking good, others not so much, yet they all brought you here to Caltech reliably, safely. That's why we are here now. Others of you came by bike, and I'm sure many of the bikes might look like this just to make sure they're not stolen by the time we leave in about an hour. Hopefully not like this. We have amazing means of transportation nowadays. Many of you may have come by airplane to Pasadena, to Los Angeles recently. And you may not know that these vehicles that you've had on now have lifespans of 20 to 30 years. In their life, they surround the globe more than 600 times. We take all this for granted. We came here tonight to Beckman Auditorium, the building on campus with the highest ceiling. 60 feet above us is a massive concrete roof. And all this less than 30 miles away from the San Andreas Fault, one of America's most active seismic zones. So, as a question for you, why are we really here tonight? Why are we here? We're here because we have materials in our everyday life that allow us to do the things we do. And tonight we're going to talk about some of these materials. Theodor von Karman was a Hungarian-American aerospace engineer who came to the States, came to Caltech in 1930 to become the first director of my department, and also one of the founding fathers of JPL. And he once said, "Scientists study the world as it is, engineers create the world that has never been." Tonight we're going to be scientists and engineers. In fact, here at Caltech, it's a little difficult to differentiate between these two species. We're all engineers and scientists at the same time. And we're going to create new materials, and we're going to understand the way materials behave. So what we're going to talk about tonight is the performance of materials. Why do they behave in certain ways? How do they deform? Why do they fail? In order to understand their behavior, which we can see with the naked eye, we have to zoom in. We have to look at the smaller scales. The coin on the very first slide was, of course, only a cartoon. In reality, we do have these many lower scales that we can look at, that we can use to understand material behavior. Going from small to large, to understand, to model, to simulate, to predict material behavior in our everyday life. And once we have that understanding, we should be able to go the other way around. We should be able to say, if I want a certain material that has properties, how can I make this? And I'll show you some selected examples for this. And of all the materials we have, I decided to talk about boring metals. Why is that? Well, first of all, I'm going to try and convince you that metals are not so boring at all. And second of all, because they're still the most widely used material we have on Earth that we're using for our technological applications, so they're very important, for a good reason. Metals are stiff and strong, which is why we can build tall structures out of them. This is the famous radio mast, Warsaw, Poland. It's more than 2,100 feet high. It was the world's tallest structure for almost 2 decades. The stiff metal frame made it possible so it could stand clearly up and not deform even under strong winds. Metals also have an ugly side, namely A, they're heavy, and B, if they fail, they often fail catastrophically. This radio mast did not cease to be the world's tallest structure because someone built a taller one. It did because on August 8, 1991, maintenance workers made a crucial mistake in the top section of the mast. They didn't secure the support wires correctly. What happened is the mast started to bend under its own weight. It kept bending, and eventually it snapped in half. It collapsed in its entirety. The remains are still on site today. It was never rebuilt. The city of Enschede in Germany holds another very sad record, namely that of the deadliest high-speed train accident of all times. What happened on June 3, 1998 was a chain of very sad events. These trains had metal steel wheels, and one of these wheels developed a crack, a large crack that grew. The wheel broke, it got stuck in the floor of one of the carts. It led to a derailing of the cart, and eventually the entire train collapsed into a concrete bridge. More than 100 passengers lost their lives on that day in the city of Enschede. And all of this because a single piece of metal did not perform the way we wanted it to be. Of course, metals are not only bad, they also lead to progress, they lead to advancement. How do we characterize the early ages of mankind? There's the Stone Age, there's the Bronze Age, there's the Iron Age. There was the discovery of new materials that led humans, mankind, to advance to a new stage, to where we are nowadays, an iPod age, or however you want to call this. And we still have these challenges nowadays. Fusion, energy from fusion is one example. If we could harness energy from fusion, we would solve extremely many problems on this planet. We cannot. But one of the reasons we can is quite simple, because we do not have materials that could contain this extremely hot and reactive mass that you have during fusion. We don't have materials to build reactors these can be contained in. Metals, of course, a good idea, but we clearly don't have one that meets the requirements. And even on a more personal level, this was the outcome of a very sad backyard project of mine last fall, when I tried to bring nails into the concrete foundation behind our house. Before I learned about concrete anchors, I'm not exactly a handyman. If only there were stronger nails that would go into concrete. They did not. They bent easily, they broke, they failed. If only there was something better and stronger. For all of these applications, metals surely are a great idea. They have good properties that we can use in our everyday life. But there's also applications where metals are not good at all. There's a reason why sports gear looks like this, and not like it might have some 5 centuries ago. Can you imagine a football player wearing metal armor? During a severe impact, a hit in a football game, the acceleration can be more than 10 times higher than what an F-16 fighter pilot experiences during a roll maneuver. This is an enormous impact energy that comes onto the player that must be absorbed. If the gear does not absorb it, it goes all the way onto the player. And if the player is wearing something like this might have been good against damaging weapons, but is not good against impact. Every player would have to leave the field after a couple minutes with a severe concussion. This is not what we want. Professor Ravichandran gave a very interesting Watson lecture not too long ago about the mechanics of impact. And this is one example that I actually saw in his talk. Birds are a major risk to aviation, to aircraft. When a bird hits an object, it can lead to severe damage. Normally, this impact energy that must be absorbed goes with the velocity of the two opponents. Of course, birds are slow, but planes are fast. Planes can go up to 500-600 miles per hour, and so when a bird hits a plane at that speed, it can lead to really severe damage if the impact energy is not absorbed properly. It can even lead to severe vibrations on the airplane, which are not good in aviation in general. These are air applications. Here are some space applications that have similar implications. What we see here is the spacecraft that brought Master rover Curiosity to the Red Planet. They landed in October 2012. I'm sure you all know about this. The spacecraft had to decelerate for more than 13,000 miles an hour down to a velocity of 0 on the ground. And JPL did an amazing job at handling this. If you had made all this out of metal, that might not have been a good idea. Of course, it's great because it's robust, because it's durable. But the impact-like loads, the vibrations that occur, might have destroyed many of the sensitive instruments on board. So we need different materials. Metal is not always the best choice. Another application that we're starting to look into now are space telescopes. This is a graphic showing the James Webb Telescope. It's planned for launch in 2018. It will go out to space and allow scientists to peek into the most distant galaxies, and especially to look into the universe's past, back to the early days. These telescopes have very large mirrors that collect signals from all around the universe. They send them onto a secondary mirror and then onto the instruments in here. What you need for these mirrors is a material which, of course, is strong and stiff. You don't want this to deform easily. But at the same time, you need something that cannot vibrate if it's being hit, for example, by space debris. Imagine you're standing in front of your bathroom mirror in the morning, and all of a sudden the mirror starts to either deform or to vibrate. You're not getting a clear image. You're at most getting sick. The same thing is what we see here. We need materials which damp vibrations, which absorb the energy of vibrations. The destructive power of mechanical vibrations became very obvious in this example, which I'm sure most of you have seen before, the Tacoma Narrows Bridge, also known as the Galloping Gertie. It was built and basically destroyed the very same year, 1940. And what happened is, due to very poor engineering design, strong winds led to what is known as aeroelastic flutter. The bridge started to bend, deform, distort in one of its eigenmodes in resonance. These vibrations became excessive, and eventually they destroyed the bridge. In just a couple of seconds, you will see how the bridge collapses. Fortunately, no one was killed. Only a poor dog who refused to leave the bridge was killed on that day. And what we see here is that vibrations can indeed have very damaging power, and we might need materials that get rid of vibrations in order to avoid something like this. And now we're going to see how it fails. The bridge starts to collapse, and it crashes entirely. Vibrations are damaging. We must get rid of them in many applications in order to avoid things like this. Metals are not good at damping vibrations. If you want to quantify damping, what you do is the following. I have a little example here. This is a slightly oversized tuning fork. This is multi-scale for musicians. And if you excite it, of course, you see how it vibrates. I can hear a clear sound. You unfortunately can't, but you can still see that it's vibrating. It's vibrating a lot, and it will do so for quite a while. That's the reason why we make tuning forks out of metal, not out of rubber. Imagine this was rubber, it would stop immediately. It's still vibrating. I'm not doing anything. So metals really have very low capacity to damp vibrations. I'm sure the first rows can still see it's vibrating. If I hit it again, it keeps doing this. Damping is important, and we quantify damping simply by saying how long does it take to remove vibrations. Now, I've been talking about stiff materials and high damping materials for a while, so let's take all the materials we have on Earth and let's look at what they do and what they have. What we see over here is the following. On this slide, on this axis, we have stiffness. The stiffer material, the more in the back we are. On this axis, we have damping. The better the material is at damping, the more we are down here. And finally, in aerospace application, we want things to be light. So we have density or mass on the third axis. The higher we are, the heavier the material. And we see metals, diamonds all up here, polymers, rubbers down here, and we start to see a common trend, and that is The stiffer a material is, the more we want to go to the back, the less damping it has, and also the heavier it is. This seems to be a common trend. And especially, there's nothing in this corner. If you want something that has high stiffness here in the back and high damping down here, there really isn't much. These two seem to be exclusive. If you want something with high stiffness and high damping, you have a hard time finding material that meets these requirements. Of course, you may say nowadays you have composites, and people do all kinds of things, but you can't really do this with composites, and the reason is the following. A composite is nothing else but you take two materials, you combine them, and you get something new that has new properties. If I take 2 points in here, for example, let's say I take something stiff, such as diamond, and I take something which is not so stiff but has high damping, such as a rubber, and I combine these two into a polymer, you get something new. But the truth is that whatever new you get, its properties will lie very close to this line. It doesn't have to lie on the line, but they will lie close to it. What this means is you can take any 2 points that you want, you can connect them and make a composite, you will never get into this corner here. It's impossible. So with normal materials, it seems to be pretty much exclusive. If you want something stiff and high damping, that doesn't exist. And so when we talk about material properties, the ones I mentioned, only some of the ones we could talk about, we will talk about strength of materials tonight and their stiffness. I mentioned the damping and their capability to absorb energy. One of the things I will mention towards the end is active materials. Nowadays, we don't want materials just to be, we want them to do stuff, to react, to respond, we want to control their properties. And of course, we want them to be light. In aerospace, we don't want them to be heavy. There's many other properties we could be talking about that I don't have time for. If you could find new materials to improve the life of batteries, you would save many energy problems we have on this planet, yet we're not talking about this tonight. Just a couple of weeks ago, we saw an interesting Watson lecture on tiny biomedical devices. If you could improve the lifetime, the functionality of biomedical applications, of devices, of hip implants, of who knows, that's great. If it kills the patient within a couple of seconds, you might have a hard time getting FDA approval. So biocompatibility often is an important issue. And there's many other ones. We want your material to be able to be produced, of course. We want them to be inexpensive. If you want something stiff, it would be easy to make everything out of diamond. Yet, if I had my lab full of diamond, I probably wouldn't be standing here. I would sell it and do something else. There's extremely many properties that we could be talking about that we will not talk about because we don't have the time tonight. Instead, we'll focus on the mechanical properties because I'm interested in the mechanics of materials and the mechanics of solids. And these are the orange ones highlighted here. So let's get started by defining some of them. And I couldn't get around to show you at least 2 or 3 equations. That's all I will do tonight. Let's start really simple. Everyone knows a spring. If you apply a force F to a spring and you pull on it, the spring gets longer by a certain distance x. And most people know from high school physics, or even from middle school physics, that the force is nothing else but a stiffness constant times the elongation. This is the stiffness. The stiffer the spring, the more force you need to deform it into a certain shape. If you remove the force, the spring usually goes back to where it was before. This is what we call the elastic behavior of a spring. Materials behave pretty much the same way. I actually brought one over here. What I have here is a tension test specimen made of aluminum in this case, and this is the kind of test device that you would use. You take it, you clamp it into a test machine, which may look like this, and you apply a force. So it's clamped down here, and we're pulling on the specimen. You can measure the force, you can measure the elongation, and what we get is a relation which, again, looks like this. The force is a stiffness times elongation. The problem is this stiffness here, K, is not really a material constant, and people realized this long ago. The reason is quite simple. Force doesn't say much about what we do to a material. If I apply the same force to a thin wire or a very thick rod, it's not going to have the same effect. So what we do is we take the force, we divide it by the cross-sectional area of the specimen. This is what we call the stress. The same for the elongation. If I tell you, yes, I ran an experiment and the specimen got about 1 inch longer, that doesn't mean anything to you until I tell you if the specimen originally was 1 inch long or 10 feet. That makes a big difference. So we divide the elongation by the original length L. This is what we call the strain epsilon. And now in the middle we have a constant E, which indeed is a material constant. That's the material stiffness, and it is named Young's modulus after Thomas Young, an English scientist, who in fact got really lucky because he was not the first to discover this constant. In fact, the 2 pictures I should be showing are probably these. Leonhard Euler was a Swiss mathematician and physicist who used the concept of this Young's modulus more than 50 years before Young. Giordano Riccati was an Italian all-rounder. He was a scientist, an architect, a musician, and he actually measured Young's modulus more than 25 years before Young actually worked in this area. Yet, for some reason, Young got lucky, so now tonight we're talking about Young's modulus instead of the Euler-Riccati modulus. Now, there's another property that I'll talk about that's quite interesting, and this is what we can see here. If you take a piece of material and you compress it, for example, it gets fatter. If you pull on it, it gets thinner. This is what we observe in everyday life. There was a French scientist named Simeon Denis Poisson who measured this and wanted to quantify this effect. So if I make it longer by a certain distance, delta L parallel, and I measure how much the change in cross-section is that corresponds to that, he could find another quantity, a constant, which we call Poisson's ratio. This Poisson's ratio tells you if you stretch a material, how much does it change in the other directions. And for different materials, we have different numbers. For metals, we usually have something on the order of 1/3, meaning if you take a metal, you pull on it, the cross-section changes by about 30%. There's one material that's kind of unique and that hits the bottom of what we can do, and that's cork, and you actually all know it. Ever wondered why there's cork in a wine bottle where there's not rubber? Well, this is the reason, because it has a Poisson's ratio of 0, which means if you pull on it or you compress it, it hardly ever changes in cross-section. Imagine you were trying to get a piece of rubber into a wine bottle. It would start to expand. So you keep pushing further. It expands more. You would never get the rubber into the wine bottle. Cork doesn't do that. That's the reason why people for centuries have used cork to close wine bottles. Anything below 0 is usually not physical. It would mean if you're pulling on something, it gets fatter, and if you're compressing something, it gets thinner. This is what we don't see in ordinary materials. A negative Poisson's ratio is something we don't normally see. Everything I've shown you so far only holds true for small deformation. If you apply a small load, of course, the spring will go back. If you apply a gigantic force, of course, at some point, the spring won't go back to where it was before. So this can't be it. And as a matter of fact, if you take the test specimen and you keep pulling to very large loads, what's going to happen is what you see here. First, nothing really happens because the force is increasing very slowly. But at some point, we can see a deformation occurring, and it's going to thin out here. This is what we call necking. The specimen gets thinner and thinner, yet we keep increasing the force. And so what happens is the inevitable. Eventually, the specimen will just break and fail. And this final part of deformation, you can even see the necking still is permanent. This does not go back to where it was before. That would be tremendous if it would go back and close the gap, but that doesn't happen. So there must be more going on beyond a simple stress equals constant times strain. This relation is much more complicated. There's a really complex behavior that we try to understand. There's many more ways how you can measure these constants, and one way that people use nowadays is indentation tests. What you do in indentation is you basically take a very tiny poking device and you poke into the material. It has a number of advantages. It doesn't destroy, it doesn't kill the specimen, but you can also measure the properties locally. You don't have to test the whole specimen. At each point where you want, you can poke into the specimen, into your sample, and you can measure what happens. What you get, for example, is the load that you need to punch into the material versus how deep you can go, the indentation depth. And what you see is initially everything is nice and smooth. This is the elastic region. If you retract the indenter, it probably goes back to where it was before. But at some point, interesting things start to happen. This is no longer a linear relation. It goes up and down, there's zigzag, there's a lot going on a very small scale. We like to understand what is going on, what leads to permanent deformation, and what deforms metals the way they do. In order to understand this, we have to zoom in. Everyone starts small. We have to look at the smaller scales. So let's zoom in. On the surface, metals are shiny and homogeneous. They look nice, polished, like a homogeneous solid. When we can't see any further, we have to use experimental techniques, so we can use optical microscopy. And if you zoom in, you see that metals actually are not so homogeneous at all. They have a whole lot of structure on a smaller scale. What you see here are very many patchy regions separated by some kind of dark straight lines. Very much looks like flying across Kansas, where you see all these farmlands underneath separated by straight lines. This is actually in the metal, and you can see this. This is aluminum, for example. Of course, at some point you can't zoom any further, it becomes blurry, so one can resort to the next technique. You can use scanning electron microscopy. If you zoom in further, what you find is that even the homogeneous regions we had before are not homogeneous at all. There's a whole entanglement of these black channels, streets, roads within the farmlands in Kansas, whatever it is. If you keep zooming in more and more, you see more detail, but of course at some point this becomes blurry too. So one has to use another technique. And the final technique that will be shown here in just a few seconds is called high-resolution transmission electron microscopy. And with this, you can actually zoom into more details. And what you will find is that, of course, all of these detailed structures are made up of atoms eventually. So all the way from the microscopic scale, we went down to the atomic scale of individual atoms in a metal. If we want to understand what all this is, what we see on all these scales, we better understand what these atoms do. So let's look at the atomic scale in metals. This is an atom, or how we picture it to be. There's a heavy core in the middle, there's electrons around them, and metals do something very interesting. If you zoom out and you look at very many atoms, they share electrons. Electrons go into what's referred to as the electron cloud very often, and now you have these heavy cores moving around. I'm going to refer to these as the atoms. And now atomistics actually is nothing else but shopping in a crowded place. You're running around, and there's people around you who are bumping into you. You're interacting. People are pushing you. People are pulling on you. And they're trying to move you, and you're trying to navigate through the crowds. And so atomistics really is nothing else but shopping. The force, the total force that's exerted on you by all of your neighbors determines the path into which you're going. So the total force determines the acceleration. And of course, the heavier we are, the slowly we're moving, which is why mass is in here as well. So now all these atoms are moving, and they also contribute energy to the material. If I'm shopping in a crowded place, I'm very energetic, and atoms are too. So atoms are interacting, and they have energy. This energy depends on the distance to their neighbors. Atoms are very much like us. We like our neighbors, but only at the appropriate distance. Not too close, not too far. There's an optimal distance somewhere in the middle. And that's exactly what we have here too. Atoms and metals interact, and what really matters is the distance to the neighbors. And they try to arrange them in an optimal way so that these distances are optimal. And what happens is this leads to very regular crystals. Because every atom wants to have a nice and ordered surrounding, this leads to metals having order. Metals really like it tidy and ordered. And if you could zoom into this level of detail, this of course is only cartoon, you would see that atoms are very neatly lined up. There's not much irregularity. They're very neatly lined up in a so-called lattice. And every metal knows exactly what kind of crystal structure it wants. This is an example where a student of mine took magnesium atoms and tried to arrange them in the form of copper. If you let this go, if you let the atoms do what they want, they will notice immediately, oh, no, this is not the state I want. I have to change. I'm copper. And this is what they do. If the atoms are in a wrong spot, it will immediately go into a new configuration that will transform. And we'll see this later on. So atoms know the structure. There's different types of structures, and these are typical pictures of what you find in metals. Chrome, vanadium, tantalum, some of the species you find, for example, in high-strength steel, have crystal structure atoms that look like this. If you take this structure, you repeat it periodically, you get a very large crystal. Silver, gold, platinum, all the metals we like to have a structure here in the middle. It's much denser packed, and it has a different arrangement. Magnesium, the one I referred to in the previous slide, is kind of odd. It has yet another structure. And every metal has its own structure, and they know what structure they want. Some materials actually can have more than one. They can't get enough. Iron is a good example. If you have iron at low temperature, it wants to be here. If you heat iron up above 1300 degrees C, it actually changes. It goes from here to here. And what happens is exactly what I showed in the movie before. The one state becomes unstable. They don't want to be there anymore, so they automatically change into the next state. They transform. And finally, if you could actually have very high pressure, then iron would even go into this one. So it goes through all of these stages. And it is this crystal structure that gives rise to many of the properties. For example, the elastic constants. If we look at this block, this is a block of copper being compressed. All the atoms are very neatly arranged, and as you push it, of course the atoms, they can't do much. They can only expand because they're lined up so neatly. Every atom is moving in exactly the direction where it's supposed to go. They're still trying to keep their neighbors at the optimal distance, so the entire crystal is expanding, and this is exactly what we see as Poisson's ratio. We push it, it gets fatter. We pull on it, it gets thinner. The same for the stiffness, Young's modulus. When you push on the material, of course you need a force to deform it. You want to press the atoms closer to each other. And this depends on the interaction. You have to press hard so that atoms that want to be further away get closer. This is what gives rise to the elastic properties. It is the crystal structure. Once you know how they are lined up on the crystal lattice scale, you know exactly what these properties are. The same for mass density. First of all, metals have very large cores, but also they're extremely densely packed here. They're not just flying around, they're in a very dense lattice. This is why metals are so heavy. There's many other properties that come from the crystal structure, but these are the ones I mentioned before. And the crystal structure is also responsible for another phenomenon, and this is the lack of energy absorption. What you see here is a copper crystal at rather low temperature, and we're pushing it on the right. Basically, here's your football player, this is the metal armor, and on the other side is the opponent who's punching him. He's punching into the material, and what you see here is the impact energy as a wave being transported through the material. There is no absorption of energy at all. All the impact energy is going beautifully through the material, hitting the poor football player on the other side. It basically looks like if you're dropping a stone into a pond and you see the waves propagating. This is what we see in metals, and this is the crystal structure that gives rise to it. But of course, nobody's perfect, neither are metals. And if you take a metal, let's say all the atoms are lined up neatly like this, I could take this and I could rotate it slightly to the left. Now the structure looks like this. It's exactly the same structure, it's just rotated. So all the neighbors, all the distances to the neighbors are still the same. It's just rotated. I could do the same to the left, rotate it this way. It's again the same crystal structure. So how does a metal know which one it wants? Well, it can't decide. It picks all of them. What we normally see in metals is different patches. Over here we have a different orientation than up there. Down here we have yet another orientation. This is what we call grains. Each of these orientations is a different grain, and they're separated by grain boundaries. We see this behavior actually under the microscope. We did see it a couple of seconds ago. These these light patches here are nothing else but the grains. The farms in Kansas are just grains, and the roads in between are nothing else but the grain boundaries. We're not in Kansas anymore. Charles Frank was a famous materials scientist who once said, materials are like people, it's their defects that make them interesting. Now, defects in humans can be of many kinds. Some of them are physical. What we see here is a dislocated elbow. It can be quite painful, but luckily it can easily be repaired, more or less easily. It really hurts, but it can be done. And a dislocation here means nothing else but the joint is not where it's supposed to be. Something is in the wrong spot. That's exactly what we see in metals as well. If we take a look at a metal, let's say this is our atomic lattice. Looks perfect, right? There's a defect in there. Can you see it? It's a little hard to see, but if you follow these red lines, you will see they're perfect over here. All the atoms are lined up nicely. They're perfect down here. But here in the middle is a half plane of atoms that doesn't belong there. It just stops in the middle of the crystal, locally distorting the crystal. Something is wrong here. This line of atoms doesn't belong there. That's what we call a dislocation. And these dislocations are not just there, they're extremely important because they can accommodate deformation. And I'll show you on the next slide how that works. Let's say you have a crystal lattice and you want to deform it. If you apply a small deformation, everything will be elastic. All the atoms are moving a little bit. If you remove the load, they will go back to where they were before. At some point, you can't do that anymore. If you keep pushing, what's going to happen is the following. The metal could take some of its atoms and move them over just by one atomic plane. This could happen. However, this is very expensive because you have to move many atoms at the same time. Metals are smart. They have a different way to do this, and the way is as follows. They punch in just the first row of atoms. You create what we just called a dislocation, meaning an extra plane of atoms, and this then travels through the lattice. So you only punch it once, and then it goes one at a time. You don't have to move all atoms at once. You just move one plane of atoms at a time. And of course, once this line has moved through, it doesn't want to go back anymore. You have created permanent deformation. Dislocations nucleate. They are created whenever you apply too much force. They're moving, but once they are there, once they have moved, you have created permanent deformation. They don't go back to where they were before. And these dislocations are everywhere in crystals. These are the three grains I showed you before, and if we use a special technique to make dislocations visible, we can actually see that even these grain boundaries are full of these dislocations of extra planes of atoms that end somewhere in the middle that are not supposed to be there. If we zoom out further, it's not only the boundaries, even the grains themselves are full of these little dislocations. All of these are planes. This is a 2D cross-section, so these are planes that come out and go into the screen that are not supposed to be there. We have many of these defects. And just to give you an idea of how many of these we have, if we take this tuning fork here, if I took all the extra planes of atom, which are not supposed to be there, I take them and I line them up, what is the length that I would get? If you do a rough calculation, what we're getting is a length that is 10 to the 8 meters. That's a 10 with 8 zeros, meaning more than twice around the equator. There's extremely many of these dislocations in that little tuning fork. Of course, these are tiny, which is why they fit in here, but there's extremely many of them. And these dislocations interact, they're quite social. This is an example where we have a piece of metal with a number of voids in them, and we pull on it. Initially, of course, deformation is elastic, nothing really happens, but at some point it becomes plastic. What the voids do, it will start over in just a moment, is they emit dislocations. All of these, here they go. All of these little things that look like ants running around in your garden are nothing else but dislocations flying through the material, accommodating large deformation. You can see another interesting thing here. When you pull on these voids, they coalesce. They grow and they go together, and ultimately they form a crack. This is the reason why in many metals, which we call ductile, when you break them, you don't see a nice and sharp surface. You actually see a very wrinkly, rough surface. The reason is because they originate from voids like this, which are not flat and straight, but that form very many little craters in the surface. Here's another example of dislocations interacting with grain boundaries. You can see these little guys flying around, but as soon as they hit a boundary, they're stopped. Grain boundaries are obstacles to dislocations. It's just like if you're running through a crowded place, you hit a wall, you can't go any further. This is what we see here. This actually is one way how people make very strong metals. You just make the grains really small, so dislocations can't go very far. Of course, this breaks down at a certain length scale, but in principle, if you make your grains smaller, dislocations can't travel that far anymore, which means you must apply more load to create new dislocations and to keep deforming the piece of material. Another way to make material stronger, goes into the same direction, is by alloying. What people have done for a long time is to alloy metals. It means nothing else but you take some other kind of material, vanadium, chrome, whatever, and you put it into the metal. And what happens is basically the same mechanism. You have this second species of atoms in here, and they form obstacles to dislocations. When a dislocation hits an obstacle, it's blocked, it's pinned, it can't move any further, so you must increase the load to make them move any further. This is a way to make metals stronger. Now, if we take a look at the length scales that are involved here, there's very many. Here we have a yellow line going from nanometers all the way to kilometers. In case you're not familiar with the metric system, I must admit I never got accustomed to your inches and yards and feet. As a matter of fact, when I first came to the States, I went to the DMV to get my driver's license. I will never forget the puzzled look on the lady's face when I told her my height was 183 and my weight was in the 70s. She just looked at me and said, "No way, honey." So to avoid any confusion here, this is about a foot, this is about an inch. This down here is about the diameter of a human hair. What we have down here is about the size of a red blood cell in our body that transports oxygen. And everything we have down here is really small. Atoms are here. The atomic distance is tiny. In fact, if you take this hair and you slice it into more than 500,000 equal slices, that thickness will be approximately close to where you get in terms of the distance between atoms. Atoms form dislocations, as we've just seen. They form these defects, and these defects are exactly what we saw a couple of minutes ago in the micrograph. These black channels that we saw within the farmlands, these are dislocations. These are planes which are not supposed to be where they are. These dislocations are contained in grains. We saw the grain structure a couple of minutes ago. And these grains, of course, are contained in materials. They are on a screw, and the screw might be sitting up here in the Eiffel Tower. So there's a vast amount of scales involved. If we want to model the behavior of metals, I mean, it looks easy. We know how atoms interact. That's just chopping. We discussed this before. So why don't we just build a computer model and model all this using computers? Well, let's do a very rough calculation. And the question is, on each of these scales, how many atoms would we actually have to model? Down here, it's apparently only a few. If you want to model something on the order of a red blood cell, you already need 10 to the 10 atoms. That's a 10 with 10 zeros. That's a lot. Something on the order of a millimeter is already 10 to the 20. If you ever wanted to model the Eiffel Tower, that's a 10 with as many numbers as you probably can't even count. That's a lot. So the question is, nowadays, we have computers. What can we do with a computer? Well, the truth is we can't actually do that much. We have limited memory. We have limited speed. If I take my desktop computer in my office and I do a calculation, I can estimate that I can be barely simulating 5 million atoms. That's the limit. Beyond that, the memory doesn't last, and also I would be waiting forever for the results. We're lucky we have a cluster here at Caltech. It's basically a connection of many computers, but even with this, we can barely do 300 million atoms. That's it. We're very fortunate to have access to a supercomputer at Argonne National Labs called MIRA. This is basically a combination of more than 200,000 computers, but even with this, you can barely model 10 to the 13 atoms. So if you compare numbers, there's no way we can ever go here. We cannot model this. It doesn't work. Of course, we're lucky because everyone knows if we were at small scales, we could use atoms, but if we were at a large scale, why would I use atoms? I mean, if in physics, in school, someone asks you what's the force on a spring elongated by x, no one would say, okay, let me do the atoms first. And you know that the force is just stiffness times x. You wouldn't do atoms in this example. So if we're large, we do this. If we're small, we do that. Sounds good? Problem is that doesn't work for many applications. And here are two examples. What we see on the left down here is a tiny microelectromechanical device. These little guys are microelectronics that you can find in all of your iPhones, iPads, iPods, everything with an I in front. There's many of these nowadays. Over here you see another example that I'll go back to in a couple of slides made by my colleague, Professor Julia Greer here at Caltech. This is a tiny structure. And both of these live on scales that are right here in the middle. They live on scales where we cannot use this anymore because these are so small you actually feel the individual atoms. But they're way too large to be atomistic. They're here in the middle. That means 10 to the 20 atoms. We can't do this, even on the fastest computer. So we have to do other things. One of the things we do is develop models that are based on coarse graining. I'll just give you a quick idea of how this works. Let's say these are the atoms in a crystal. We have a grain boundary in the middle. This is one orientation, that's the other one. And we have two dislocations over here. You can actually see them. Here's a line of atoms ending. Here's another line of atoms that ends somewhere in the middle. Now, close to these defects, we might need all the atoms, because these might be moving, they have strange neighbors, and so forth. But all the other atoms, the gray ones, they look all the same. They all have the same neighborhood. So why don't we do the following? We have general elections, and we elect representatives, the red ones. We call them the representative atoms. And these now speak for their neighbors. They get a weight, and the weight depends on how many gray atoms you speak for. And now what happens is pretty much what happens after general elections. Once you elected them, we have to do what they want. So if you have red atoms, which are the representatives, and you have some in the middle, if the red ones are moving, we simply say the white ones are moving conformingly. We interpolate their positions. And based on this, we can model things using the red atoms only, using only the representatives. We can forget about everything else. And with this, we can target large systems. This is an example when you look at these individual fingers of the microelectromechanical devices. They are very prone to failure at certain spots where they can break easily. There would be no way to model this using atoms. But you can easily model this if you coarse grain. If in certain regions where you're sure nothing's going to happen, you use only very few atoms. But in those regions where things are going to break, you use very many atoms. We just condense out many atoms. We don't use them all. This is atomistics without all the atoms. It's called the quasi-continuum method. Another example is nanoindentation. I mentioned this before. This is the tiny poking device. We're punching into a material, and what we're seeing here is what actually happens, what you cannot even easily see on our microscope, and it will soon start again. So here we're punching into the material with a spherical indenter, and at a certain point what you see is these loops form. These are nothing else but dislocations. They are extraplane of atoms which are not supposed to be there. We're showing them here. Of course, everything here is full of atoms. We're just showing you the ones that are interesting. These are dislocations. So what happens here is at a certain point, it's not elastic anymore. You form these defects, you form dislocations, you permanently deform the crystal. So if you look, for example, at the force versus indentation curve, that's the one I showed you experimentally a couple of slides ago, what we see is at the beginning, everything is nice and smooth and elastic. When the first dislocation is nucleated, you see this drop in force. You see many of these. And all of these drops are nothing else but a defect is created, it moves. At some point, it can't move anymore. The next defect is nucleated, it moves, and so forth. So these defects are really important if you want to understand the behavior of these materials. And just to give you an idea for this indenter, this is where the indenter hits. Over here, we have all atoms, but as you go away, we coarse grain. We don't have all atoms anymore. We only pick a few atoms as representatives, and these are the ones that we then have in the model. The number of atoms, of actual gray atoms contained in this simulation on the order of 5 trillion. And just as a reminder, this was done on our small computer here at Caltech. Just minutes ago, I said we could at most do 300 million. So with this technique, we can get rid of very many atoms, but the accuracy is very high. We can still capture the important phenomena. With this, we can bridge from very small to very large, from atoms to the big scale. And so what I've tried to tell you so far is how we can go from microstructure to macroscopic properties. We talked about the crystal structure being responsible for the elastic behavior and their interactions. We talked about why they're heavy, why they're so bad at damping because of the crystal structure. We talked about defects and how these defects nucleate, form, and interact when you keep loading, when you get permanent deformation. This is where the defects become important. We already talked about briefly 2 ways to design materials, namely by changing the grain size or alloying, putting new particles as obstacles to dislocation into the metal. These are traditional ways. What I want to talk about now is design of new materials. And to do this, just like to briefly review how one designs materials, how one has done this, because this is not new, the business. People have done this for a long time. I'd like to explain this by a popular family here in the States. A long time ago, what people did basically is take different materials, and go to a lab, put them together, you get a new material, and you learn what it's like. This is the alchemist approach. Of course, over time, you learn. You develop a knowledge base. You have books. We have Google nowadays. So if you want a material that is stiff and strong, has high damping, and a low weight, we look into tables. We try to find the material that we need. What we do now is we develop computer models. We have models that allow us to predict behavior of many atoms, to predict the macroscopic behavior. Where we want to go in the future is we want to have models that allow us to go the other way around. Let's say you want a material that's stiff and strong, has high damping, lightweight, is green and tastes good, or something like this. How do you make this? We really want anyone to be able to push a button, and what you get at the end is a certain material. We're not there yet, of course. This is in the future. One's trying to get there. And I'm only a very small player in this business. There's millions of people around the world working on this heavily. What I'd like to show you are a few examples of how we can actually make materials that have interesting properties. We're not already at the stage where you can change individual atoms on the smallest scale. We're not there yet. We can't easily do this. But we have capabilities to make materials that have interesting properties. Some of them are structural, and I'll show you what exactly I mean by this. Others are interesting composites. So let me show you some examples. Structural materials look like this. This is a nanotruss structure made by my dear colleague Julia Greer here at Caltech and her group. And they fabricate these structures. They are nothing else but very small truss structures. Each of these guys here is a hollow tube. And just to give you an idea of the length scale, this is a human hair on the same scale. So these are really tiny. The great thing about these structures is you can design them however you want. This is not atoms. These are trusses. So you can arrange them in whatever way you want in order to get certain behavior. And one of the truss structures that we've been looking at, for example, is the one that you will see here. And just to give you an idea of how small it is, we put it on a quarter, just for show. What you see here is a truss structure that we design on a computer. And what you can do, for example, is you can compress it, and you can see what happens. How does it behave? And you see interesting things. This is the truss structure I just showed you. If we now compress it from the top, one at a time, what you see is you compress it, but at the same time, it shrinks laterally. It doesn't expand, it actually goes in. So we've created something which, when you compress it, it doesn't expand anymore, it shrinks in the cross-section. That's what we call the negative Poisson's ratio. We said is not possible a couple of slides ago. And to show you the effect a bit more nicely, this is the same in 2D. This would be a standard structure. If we're compressing it, it becomes fatter. If we're stretching it, it becomes thinner. This is the typical behavior. If these were atoms, we couldn't really change the atomic structure, but these are not atoms. These are trusses. We can move them around. So why not arrange them like this? And now if you pull on it, it expands laterally. If you contract it, it also shrinks laterally. With this, you can make negative Poisson's ratio, no problem at all. And just as a side remark, please note that these little voids here, they actually close when you compress it, and they open up when you expand it. This is one of the reasons why this is interesting for many biomedical applications, as I'll show you on the next slide. What we see here is an example of how Andy Alderson's group in Bolton actually makes this for foams. This here is a conventional foam. If you pull on it, which is what the hands are doing, it becomes thinner, and if you compress it, it becomes fatter. Down here, we have one with a negative Poisson's ratio, which is known as an oxidic material. If this is the original foam and you're pulling on it, it doesn't become thinner, it actually becomes fatter quite a bit. You can do this with foams, and Julia's group here at Caltech can also do things like this with trusses. It's a similar arrangement. You have a negative Poisson's ratio. Now, what are the applications of this? One of them is this pictured over here. Imagine you have a bandage, which is made of this material, and it contains some medication. You put it on the wound, and as the wound swells, all these pores open up, so it can release the medication automatically into the wound. It absorbs the blood, and as the wound swelling goes away, it closes its pores again. So there's no medication that's going out anymore. The blood is contained on the inside. That's one application where you can use it. Another one are biomedical stents. These are being used very widely nowadays to open up clogged arteries, blood vessels. Whenever you have plaque in there, you need to open up these arteries to prevent further damage. So what medical doctors do is they insert a small stent, a piece of metal, which is then basically blown up. It expands to open up the clogged blood vessel. And this material, these oxetic materials, are ideal for this. You just take a very small piece of this oxetic material, you insert them into the blood vessel, now you pull on them and they expand. And based on this, you can expand the artery in exactly the way you want. Makes it really easy. These truss structures have very many interesting properties. One of them I'd just like to briefly mention here is damping. Remember how a while ago I showed you a movie which looked exactly like this, but it doesn't have these black holes. And we saw how the impact energy went through all the way. Now what we did here is a thought experiment. We made little holes into the material. This is still a copper single crystal, but we introduced periodic holes. What you see now is a scattering and dispersion of waves. The waves don't go through anymore. The football player is back here at the other end. There's hardly any wave coming through. If you have a periodic structure and you use it wisely, you can actually absorb energy. You can create damping of impact, damping of vibrations as well. And we can do this with truss structures. These are two examples that we modeled in the computational lab. What you see here is one truss structure up here, another one down here. They're slightly different. The order of trusses and the distribution of mass is slightly different. And we're pushing both of these on the right-hand side. The football player opponent is coming in and is pushing in from here. What you see down here is the wave is just propagating through. These blue and red wave packages, amplitudes, just go through. The poor football player on this side is getting the full load of impact energy. The lattice on top doesn't do that. We're hitting it pretty much the same way, but what you see is the wave is damped out. It's scattered, the wave gets dispersed. It's the periodicity of the lattice which we can use to attack broad frequency ranges and prevent them from going through. So with these, you can make structures, you can design their elastic properties, you can make them do funny things like a negative Poisson's ratio. They're extremely light, by the way, because these are hollow tubes. They're extremely lightweight. And at the same time, they are still metal or ceramic, so they can still be pretty stiff. This is a way how you can make materials that have certain properties. Gesundheit. Here's another example of negative Poisson's ratio now for a composite material. What we see here are stiff inclusions in a compliant matrix. Normally, this shouldn't be doing any interesting. What we see is the following. As you compress it, the movie is actually playing, these inclusions start to rotate. If you expand it, they rotate the other way around. You can see these little guys slowly rotating. If you can't really see the effect, I'm going to zoom out and show you a bigger one. If we compress it, you can see how it also goes in the lateral direction. When you expand it, you can see how it also expands in the lateral direction. So here you have another simple example of how you have to arrange materials, how to make a microstructure to get interesting properties on the macro scale. You compress it, it gets thinner, you pull on it, it gets fatter. We have another oxidic material that can easily be designed. Composites are interesting materials for many reasons. As I said at the beginning, you take two materials, you put them together, you get something new. One of the problems that I mentioned early on is they don't really do anything interesting because you can't get into this yellow corner. Let me show you one example of materials that actually act. They react and they do something quite interesting. What we see up here is the crystal structure of a material known as barium titanate. It's actually ceramic, but it has the same structure as these precious metals I showed you before. Barium, oxygen, titanate atoms all around. This is the crystal structure at high temperature. Now what happens is when you change the temperature to low temperature, this structure actually changes. It does it exactly the way I showed in the movie. The atoms don't want to be in their state anymore. They deform and they go into a new state. And this new state looks a little bit different. It looks like this. That's what we call its trigonal state. You can see that the nice cube is distorted into this unit cell over here. The titanium atom moved a little bit over to the left. It has deformed. We can do one more thing. We can apply an electric field to this. If you apply an electric field, what happens is the atom is rearranged. The titanium atom hops over to the right, and the oxygen rearranges as well. If you invert the electric field the other way around, what happens is the atoms go back. So it can keep doing this back and forth, and you can basically switch the atomic structure. Based on this, we have a way to change the material externally. All we have to do is change temperature or apply an electric field. This makes materials active. Now, we still can't get away with the problem I mentioned early on. So if we make a composite, let's say we take these barium titanate, for example, particles, we put them into a metal, and we have a composite. Okay? If we look at our chart from the beginning, that should be pretty boring. Barium titanate is somewhere back here. Metals generally back here. Tin has a slightly higher damping, so they're both back here. If we draw a line between them and connect them, we're not getting anything interesting. We're no way getting into this back corner here. But now something interesting happens. When you have barium titanate enclosed in the metal, and you change, for example, the temperature, the barium titanate realizes, oh yeah, I want to be in this different state. I want to transform. I want to do exactly the dance we saw before in the movie. But it cannot, because it's trapped in the matrix. The metal around it keeps it from transforming, and all of a sudden we have kind of a forbidden state in the material. It wants to be in a different state, but we keep it in this high temperature state, for example. We lower the temperature, the material wants to go here, but the metal surrounding it prevents it from going there. We now have a composite where we have metal, but in here we don't really have our barium titanate anymore. We have some kind of weird barium titanate that is in a forbidden state that you normally don't see. And what happens is when you use these unstable states, the general principles don't hold anymore. You draw a line, you combine them, and you have to stay close to that line. What happens is the following. When barium titanate becomes unstable, it develops what we call a negative stiffness, meaning you would in principle have a negative stiffness number. And so what we have here is a material with a high stiffness and a material with a negative stiffness. Normally, when you add a positive and a negative number, you get something close to 0 if they're similar. In this case, that's not true. Positive plus negative actually equals a lot. And we can do this in the lab. You can make these composites. You take tin, it's easy to melt, so you put the particles in, you cool them down, you get a composite, and you can see properties like this. If you change the temperature, out of a sudden, what you see on this scale in blue is the stiffness, and on this scale in white is the damping. And out of a sudden, you see this stiffness skyrocketing by orders of magnitude. This is a log scale, so we start down here, it increases by a lot. Just for reference, this is the stiffness of steel, the stiffness of diamond, the one I was bragging about early on, if only we had that. We can go beyond this if we make use of the fact that we can use that unstable state. And at the same time, the damping also goes up quite a lot. So you have something which is stiff, but at the same time has the ability to damp vibrations. This is the temperature control. You can do similar things with the electric field. If you take this barium titanate, you apply electric fields, and you switch the electric field back and forth, you can use this to create large damping. This is an example where we apply electric fields. And what you see here on this axis is the damping, the capacity of the material to damp vibrations. Normally, it's pretty boring. We're somewhere down here. But as you change the electric field appropriately, this increases by more than 600%. So you have a material that you can use in applications, in aircraft, in spacecraft, wherever you want, that has pretty boring ambient properties. When you push a button, when you change the electric field accordingly, out of a sudden, its properties change dramatically. You can have huge damping. For example, in a case of space debris hitting an object out in space, in case of a disaster, in case of an accident. You can tweak the properties. We've made the material active. All we need is change the electric field, change the temperature, and the material responds. It does things that we want. We can control the properties. And so if we look at this map again, what we find is that the two materials I showed you, or actually the material I showed you with temperature and electric field control lies somewhere back here. The first one I showed you on a temperature control actually even lies outside this range. It's extremely stiff and has high damping at the same time. When you use electric field control, we're ending up somewhere over here where the stiffness remains pretty much the same, namely that of a ceramic of barium titanate, but the damping goes up quite a lot. So we can actually go into this yellow corner. There's no problem. You just need to have a sophisticated way to do this. So what I tried to show you today is how structure and material properties are related. We talked about how the crystal structure of individual atoms leads to performance, to stiffness, to lateral expansion, what we call Poisson's ratio, to density, to weight of metals, why metals behave the way they do. We talked about why and how they can deform permanently. They form defects that move, that interact, and eventually, of course, they fail. You may have voids that coalesce and grow, and then you have a crack, and then it fractures. These are all ways how the structure influences the properties. And then I showed you a bunch of examples where we can go the other way around. If you want something interesting, if you want something that has a negative Poisson's ratio, something that has very high stiffness and high damping, or a tunable damping, where all you have to do is tweak a little button, the damping goes up, we have ways to go the other way around. There's still a lot that needs to be done to eventually go to the point where you can modify individual atoms. Of course, what we want by the end of the day was Homer Simpson pressing a button and us being able to say, we want a material that has this and this and this property. How do we make it? And the computer tells us it's done in an hour. That's what we want. We're not there yet, of course. And Richard Feynman was a famous Celtic physicist. He had a talk at an APS meeting in December of '59, more than 50 years ago, on December 29th. I'm still amazed there were APS meeting on December 29th, but apparently that was the case. And he gave this famous talk called "There's Plenty of Room at the Bottom," where he basically wanted to say we have to go to the small scales and make things smaller because this is what will drive discovery and will push the frontiers of science and technology. Now, we're more than 50 years away from this, but still there's apparently plenty of room at the bottom. There's plenty of room in the middle. There's plenty of room everywhere. There's much that can be done. I try to give you a brief flavor of what we're trying to do and what needs to be done in the future. And so to complete this here, we came from trial and error in the lab, building computer models. That's where we are nowadays. Where we really want to go is being able to design materials by the push of a button. Of course, to get there, we need way more discoveries. We need bright minds. And of course, we need funding that we're very grateful for. And so at the very end of my talk, I'd like to acknowledge all these that have contributed. First of all, these are the students and postdocs who have been in my group for the past 2 years, or 2.5. I'm extremely grateful for them. They're probably the greatest team I've ever had. They have contributed to this, and many of them have suffered over the last few weeks to make these pictures and movies that I could show today. I'd like to thank them very much. And then, of course, there's a number of collaborators across the world, some in Zurich, some in Wisconsin, some here at Caltech, that I'm extremely grateful for their advice, for their collaboration. And, of course, funding a number of agencies in Caltech that have supported us to date. And so with this, I've come to the end of my talk. I would like to thank you all very much for coming. There are no official questions. If you have any, please feel free to come up to me to the podium. I'd like to thank you for coming. Have a good night and get home safely. Thank you.